Good day, everyone. My name is Laura Horvath. I'm the Director of Product Marketing at Appen, and I wanted to welcome you to our webinar today entitled Building the Road to the Future with Training Data for Autonomous Vehicles. In case you're not familiar with Appen, we collect and annotate training data for our customers to deploy AI projects. We support a variety of data types: text, video, image, audio, etc., and we cover, the complete breadth and depth of use cases out there. We do this through what we think is a really unique three-point approach. Number one, we've been doing this type of work. We've done in the business for 20 plus years, starting with our roots in translation and transcription. And we have incredible expertise, everything from linguists to machine learning data scientists available to us and our customers to really deliver really high quality training data for their projects. We have a very large crowd of over 1 million skilled contributors with a variety of languages and dialects and locations available, so we can always find the right contributors to do annotations for your projects. And then finally, we have the industry-leading technology platform to really ensure that your quality as well as scalability and efficiencies to be able to do this data collection and annotation in a very efficient and productive way. We have, as you can see, this is just a small number of our customers, but we cover a variety of industries, and we partner with just a tremendous amount of customers globally to really provide them to give training data to give them the confidence to deploy their AI projects. So finally, I'd like to just quickly introduce our two main speakers today. First, we have Dr. Kuo-Chien Lien. He is our head of our computer vision group in our engineering team. And then next we have Dr. Liz Otto-Hamel, who is our product manager for many of our annotation tools that are focused for the autonomous vehicle market. With that, again, thank you for joining us today, and I'll turn over presentations to Kuo-Chien.
Hello, everybody. So we're gonna first talk about autonomous driving labels. Yeah, I'm personally so thrilled to witness this paradigm shift in car industry. We have seen all of the car companies start switching their gear to electric vehicle, and all of the car companies are investing more or less on autonomous vehicle. One big news last month is Tesla is most valuable EV and AV automakers in the world. They released their FSD, or Safe Driving System. This is a very intriguing idea that's featuring the traffic light detection, stop sign recognition, and so on and so forth. And yeah, this is for sure bringing us one more step to the future of autonomous driving. It also got mixed review. What does Tesla really mean by full self-driving? Is really full self-driving ready? And we can see by SAE definition, there are 6 levels of autonomy in autonomous driving. Level 0 is no autonomy at all. Level 5, we can see we completely remove human drivers behind the wheel. The car can drive itself by any time, any place, while the humans in the car can hands off, eyes off, and minds off. So from this point of view, we can see Tesla FSD doesn't really reach the level 5 yet. Probably not even level 4, which is defined as the car can drive itself without any human in some certain environment. The good news is level 4 is indeed coming, and it can be very soon. In this year, we have seen the handful of companies already received the California DMV's permission to remove their safety drivers behind the wheel. They can do some certain driverless testing on a certain public roads in California. This is level 4. And in China, we also see many companies start commercial robotaxi services in some major cities such as Shenzhen, Shanghai, Guangzhou, Beijing. This is very exciting. During this operation, each of these level 4 ready vehicles can generate terabytes of data every day. Most of these are from the sensors such as LiDARs and cameras and radars. And some other can come from, for example, 5G remote control signals. Car companies then can consume this data and make these autonomous driving systems more and more intelligent. This is what we plan to share in today's talk from a data company's point of view. So we start from some use cases. Where do people try to bring the AI into this automotive industry? Number one, I would say, is safety. About 1 million people are killed in car accidents each year. And very naturally, one expectation to the next generation of car is it needs to be safer. That is probably not a fair statement, because car itself is safe. Most of the car accidents are due to human errors rather than malfunction of the car part. Thus, how to use AI to assist human drivers to safely maneuver or eventually removing the human driver completely is the goal of automotive industry is pursuing. And assistance, this has brought us so much convenience. Without the need of moving my fingers to type anything, I can use voice commands to search the web, search the map, and find nearby gas stations, for example, and also make phone calls. And this is super powerful thanks to this speech recognition system. Personalization. A car is not just gonna assist you, but want to assist you in your preferred way. The car can memorize the height of your seat and adjust it. It can memorize which route you take from your home to your office, and also memorize how you park your car. And the car can accommodate all of this for you. We're going to talk some more cases we have seen very often recently. One use case is the in-car driver monitoring. So some of our customers have installed these inward-facing cameras in their car, such that they can detect and track the driver's face. On the driver's face, they further use AI to detect the facial landmarks, such as these eyeballs and also left eye, right eye, mouth, noses, these kind of things, so they can determine the focus level of the driver. This is very helpful. And remember, this system needs to be working for all gender people, everybody, and in all kinds of weather conditions, lighting conditions. Another use case is HD map, high definition mapping. Some of our customers use AI to understand important roadside objects such as traffic signs. The human reads traffic signs in order to know the driving policy and condition of a section of the road. So do cars. Is there a speed limit? Is there construction ahead? Is there any slippery slope? All of this information is going to be very useful on the map. And our partner try to collect this information and learn better AI. In addition to static objects, self-driving cars also need to be able to detect dynamic objects on the road so that the collisions can be avoided. And it includes cars, pedestrians, like you say here, but also could be animals or any movable objects, 360 degree around the ego car. if this doesn't sound complicated enough, I need to mention that many of our clients are interested in nested ontology, which means a car category can be further divided into a sedan, a truck, a van, or ambulance. And pedestrian class can be further divided into children, adults, or adults pushing a stroller. So all of this actually makes sense because different subcategories of objects can perform very different types of behaviors. And our partner companies are interested in this. Especially the motion patterns, So AV companies need to understand all this information all the time so that the car can plan its path accordingly. Now you can see a huge amount of data is needed just to barely show the AI system the complexity of the real world. And next slide, Liz will talk about data, how company and try to collect training data for spinning up the automotive AI. Please.
Great, thanks, Cochin. Yeah, thanks for sharing those use cases. And now I'd like to talk a little bit about the actual training data collection and annotation process. Some questions you might have when thinking about training data for AI and automotive AI is, do you have the right data to train your models? Does the data represent the deployment context of the AI? And, is the data high quality? Does it have high quality labels attached to it? So we'll talk about some of these considerations. So starting from the beginning, where does this data come from? The data can come from different sources. Some of those include sensors attached directly to vehicles, either on the outside or, as Cochin mentioned, on the inside of cars. There's a number of different types of sensors. So these can include cameras with different types of lenses at different angles, getting different views, LiDAR sensors, radar sensors, and these are all collecting huge quantities of data, as Cochin mentioned as well, up to terabytes of data every day for a given vehicle. And all this data needs to be synchronized. So you can either build your own platform to collect all this data or buy specialized data collection platforms from vendors. Alternatively, depending on the type of data and the use case you're supporting, you may be able to use publicly available data sets for ramping up an AI project, or you could potentially approach data vendors. And we'll talk a little bit more about that. But basically, this data sets in general, having them representative of the production situation, these are all big challenges associated with having the appropriate data. So the data need to be localized. So for example, if you're talking about audio data, you're going to want to be sure that your data represent the languages and dialects spoken in the markets where you want to deploy your product. And that also includes, that's a similar consideration for other types of data as well. So for example, if you have your autonomous vehicle collecting camera data, you train it on data from streets in Europe, the street signage, the size of the lanes, the placement of road furniture. This is all going to be specific to the streets of Europe. And then when you want to take that vehicle and have it drive around in North America or Asia, these are going to be different situations with different considerations. So it's always important that the data represent the production situation in which you want to deploy your AI model for your product. The data need to be comprehensive, so they need to cover all kinds of edge cases, and this is something that we often see our customers discover during the process of having their data labeled. They unearth edge cases that weren't obvious to begin with. And of course, as is always important, the data labels need to be high quality. So data needs to be labeled appropriately according to your needs or for how the logic for when the labels are applied. One thing we did want to mention here, though, is if it turns out that it's not immediately cost-effective to begin a large custom data collection project, it's also possible to purchase so-called off-the-shelf data sets from vendors. These can be helpful for the reasons depicted here. Speed, these are available immediately. It's not taking time to collect custom data. As I mentioned, they can be much more cost-effective. They have scale built into them, so you can buy a large data set from the get-go and have enough data to train models to kind of get from ground zero to ground one. And when you purchase these from data vendors that have years of experience, you can trust in their expertise and you can trust that these data sets are very high quality. But this type of purchase can also begin a partnership with such a data vendor, which can allow you to further scale that use case. And just as an example of this, Appen does offer these types of data sets, and we have one that we just wanted to highlight here, which includes street signs, which could be used to train a model that's trying to recognize and understand these street signs. There are multiple languages represented here, and just a few examples shown on the slide. But we did want to talk also about custom data collections and custom data annotations. This would be the next step in the process after collecting that data initially, and there are some considerations that you're going to want to think about as you embark on this process. So one is just, what do you want humans to recognize in these images? So what are the sets of labels that you'll ask humans to apply to your images? And we often see with customers that this list changes as they go along in their process. They may add more classes. They may think that they've covered all the cases of interest and just added, like an other category. But when they find that annotators are putting a lot of labels in that other category, they find that they actually need to create a new class and further clarify the project. Other considerations include what format you want the annotations to be made. So do you want to apply, so for images, for example, do you want to apply labels at the individual pixel level, or would you prefer to apply labels in the form of shapes, polygons, ellipses, lines, dots, bounding boxes? And that question relates to how you would like to consume the output data. Would you like to get whole image masks as your output, or would you prefer to output coordinates of those polygon shapes? And then how do you want to handle those edge cases, and how can you instruct humans to properly account for the edge cases the way that makes sense to you for your project? Did also want to mention that this type of labeling can be very time consuming, especially if you need a label applied to every pixel. And so another important consideration is just to think about the tooling that your data vendors can offer to assist with this project, and whether it includes features that will enhance the efficiency of the labeling process itself. So as an example, when you're talking about labeling videos, of course, the scale of this labeling process just increases significantly. You have to apply labels to every frame. And in that case, it can be helpful to have features that make it so that annotators don't have to tediously apply the same bounding box, for example, to every frame in a video. And when they apply a bounding box to a first frame and a bounding box to a later frame, then the frames in between can have some kind of assumed position for that bounding box, which annotators can adjust as necessary. Or machine learning can be brought in that can predict the locations of the appropriate of the bounding box in question in subsequent frames, given a prediction given a human annotation on an initial frame. So these sorts of features can make a huge difference in the overall cost of such a project, which is of course always an important consideration. I did want to mention other types of solutions or this issue of efficiency and cost, one thing that we've done at Appen is made it easy for customers to bring a state-of-the-art model's predictions to an annotation project as a first step so that labelers don't have to create these masks starting from zero. They can actually start from a model's prediction and just adjust that prediction in the places where it's showing that it has lower accuracy. We have this feature available in our platform for a few use cases that we're showing here, including pixel labeling, semantic segmentation for street scene images, and also face landmark detection for images. And this is a feature that we're growing to all kinds of use cases on our platform. And there are similar considerations for audio training data and its annotation as well. You'll want to think about how you can describe the types of acoustic events you want to recognize in the data and what features are available for that. An important consideration is always support for a wide variety of languages and dialects, again, because that localization piece is so important to the success of your AI deployment. Additionally, it's always important to achieve high quality training data, and so you're going to want to look for vendors that offer quality control features either directly in their tooling or as secondary steps later on. So for example, spell checking if we're talking about audio transcription. And finally, again, that the tooling has available any possible machine learning related efficiency features. So bringing predictions to annotators as a first step is one way to handle that, but there are others as well. And from there, I wanted to pass it back to Cochin to talk about some of the considerations that are particular to LiDAR-related use cases.
Yes, thanks, Liz. So another important modality in autonomous driving is LiDAR. LiDAR stands for light detection and ranging, and it's an optical device that can be used to measure the distance and angle, velocity, reflectivity of a target. So here we provide a snapshot of our 3D point cloud tool that we recently released. In this figure, we can see LiDAR point cloud along with a camera frame. And on the LiDAR point cloud at the bottom right panel, there is also radar velocity vectors overlaid on top of that in yellow. So we find a lot of our clients are interested in data annotation in all of these modalities. Given these different modalities, there are two things always coming when we start to annotate this data. The first is how to describe an object of interest in 2D camera view and also in the 3D world. We have seen in 2D, people usually try to do either pixel level semantic annotation or like here in this rectangular shape of bounding box. And in 3D, there's a synergy. We usually see our clients try to do cuboid annotation. And there are some other kinds of, some other fashions of annotations, but the cuboid plus 2D bounding box is the most often seen. And in terms of attributes, people very often not just interested in this geometry, length, width, height, but also the attributes. That can be involving the status of these objects, for example, whether the sky is moving, whether the car door is open, or whether this car is performing cutting in. And all of this information are super critical when your self-driving car driving down to the road. Another thing we need to consider is to relate the geometry and attribute features across 2D and 3D. And there's sometimes a question whether we want to do this. The reason people tend to do this is obvious, because if we can synchronize all of this annotation, including 2D bounding box and 3D cuboid, then we can better understand what is happening at this moment right now. But not every sensor suite is perfectly calibrated, spatially and temporally. So in this case, when you project your 3D cuboid into this 2D view, there might be some offset. And to conquer this problem, we find it's very helpful to have a feature to allowing the human rater to slightly adjust the 2D annotation decoupled from the 3D annotation. More than the 2D rectangular shape, a lot of real-world things cannot be described in just cuboid or bounding box. For example, the bushes or layer markings, and also in a rainy day, you may have a lot of false detection on the ground due to reflection. Also, some of the customers are interested in particles flying in the air. So all of these are not easily described by using one or a few cuboid shapes. This is why we also offer this semantic segmentation tool to help our customer to give proper labels and object ID to every single LiDAR points in this LiDAR point cloud. So the best practice we found for high quality training data, first of all, is job design. Job design is always the most important thing. Starting from day one when we engage with client, we need to properly define what is the successful criteria, how much accuracy they care, what kind of ontology we want to do our annotation. And this is an iterative process. We need to keep monitoring the quality and give feedback. For example, the edge cases that both us and our client didn't thought about before. And also we need to do continuous improvement on the tool and on the spec. These things I consider the most important successful criteria that we need to do. And some other key elements we found is very important include the contributor targeting. As mentioned in the beginning, Apple has over 1 million open cloud contributing in annotating your important data. Also, we have a few secure labeling facilities all around the world. All of these managed service can guarantee high quality and very instant feedback between Apple and your PM. And test question is a good trick. We use test questions embedded in your real client's data to make sure our annotators keep focusing on these annotation job without making much mistakes. We also have in-house auditing team to keep monitoring all of these annotation result. Occasionally, if the client is interested, we also invite client's PM to log into our platform to do the auditing together. And this can be subsample data, not necessarily all of the frames and all of the points. So we find it's a very helpful process to help ourselves and help our client to understand what is going on and what can be further improved. Here we want to show an illustration of our quality flow. Start from the beginning, we have machine to do some pre-filtering or formatting to ensure your data can be properly formatted and fit into our system. Next, we're going to involve both human and machine in this pipeline multiple times in several locations. That includes probably machine pre-annotations. Like you see in previous slides, we can use machine learning algorithms to pre-annotate millions of pixels in the image before human touch it. And then human can start to refine this pre-annotation. And in this runtime, human can get instant feedback from machine learning algorithms running in the background. For example, this keyboard is not in a proper shape or proper size, or this category might be wrong based on the machine learning algorithm's decision at the background. And human raters can receive these feedbacks instantly, adjust their annotation accordingly, and this cooperation can run smoothly in multiple iterations in case some of the annotation got rejected by our reviewers. So yeah, these smart validators also is very helpful for features in our tool. So once we have implemented this quality flow, we found we always can provide over 95% of accuracy of data to our clients. And here we're gonna let these to tell you how we future-proof our data.
Yeah, great. Thanks, Cochin. Yeah, so future-proofing your data. So what do we mean by this? What we really mean is just, you've made this investment in training data, you've trained your AI models. Like, how can you ensure that your models are going to be successful in the future? What we see in this case is commonly known as data drift, or also called stale models. And what can happen is, you can train a model with a set of training data. As I discussed earlier, you may have your autonomous vehicle driving around in the streets of Europe successfully, and it's navigating the roads. However, what you'd really like to do is start selling this product in a different locale, for example, in Asia, and suddenly when you let the vehicle loose there, it's no longer able to navigate appropriately because its models have been trained on a different set of training data, and things have changed, and it's no longer able to be successful there. So, this can really happen based on this type of change in geography. It can also happen because climate has changed. The weather is different. This affects the sensors, and the car is no longer able to recognize objects with the same fidelity. And it can happen because of differences in language or even dialect, or accents, the way people speak differently. So that can be the case for audio data. And so how do you combat this type of problem? Well, one thing that we've seen that works well for our customers is to just keep that training data flowing. So gather new types of data, gather data that's relevant to the cases and situations where the models are not performing with high accuracy. And one thing we see our customers do on our platform is integrate with our APIs. This helps increase the throughput of the whole data collection, annotation, model training process by automating the movement of data in that pipeline. Another thing that a few of our customers do, and we do get a lot of questions on, is active learning. So this is the process of prioritizing the data to be annotated, basically showing showing the models more examples from situations in which they were getting confused previously. So just training up, focusing on the error issues for the model. And this can be one strategy to combat the issue of, data drift or stale models or your model misperforming in general. And another thing that's important that just needs to be said here is it is important to work with technology partners who can support all parts of this exploration, who can support different types of use cases and be flexible when you need to change the description of your data or how it's labeled, who can grow and support you and support your scaling up, support your expansion into different geographies, representing these different climates, and basically work with you to support your needs as you discover them. And I think that's all we had prepared to say today.
Thank you, Quo-Chin and Liz. Really fascinating information that you shared with everyone today. If you have any further questions for Quo-Chin or Liz or anyone at Appen, you can just quickly email us at the easiest email ever, hello@appen.com, with any questions, and we'll be happy to get back to you as soon as possible. Again, really appreciate you joining us today, taking some of your time to kind of learn from our viewpoint around how to kind of go forward, where they think the autonomous vehicle market is going to go and what are key success factors for it. So thank you again for your time.